Hi guys, our article is application of simultaneous saccharification and fermentation SSF for viscosity reduction of a raw sweet potato for bioethanol production and laboratory pilot and industrial scale. Tables of contents. First, introduction. Second, materials and methods. Third, results and discussions and conclusions. Introduction. The use of alternative sources for bioethanol production has gained great importance, though the need to reduce depends on fossil fuels. In this study, and sacrament service was used for the fermentation of real sweet potato, though the simultaneous saccharification and fermentation SSF process. Johansson and efficient provides detailed characterizations of both the microorganisms and the raw materials used was carried out. Microorganisms and growth conditions. The strain Saccharomyces cerevisiae CCT CCM 206111 was selected for its high tolerance to demanding fermentation conditions. Thermophilic in Turin and Turkey osmotolerant, resistant to ethanol concentrations about Turin. Cultivation and maintenance conditions. Cultivation grow and GPD medium and that 32 C and 50 RPM for 12 hours. Maintenance sorry in solid GPDA medium and 4C with subcultures every 2 months. And GPDA medium composition. Jet extract 5, peptone 5, dextrose 20, agar 20. Characterization of the raw sweet potato. A detailed characterization of the raw sweet potato used the process was performed to determine its availability as raw material for bioethanol production. Analyze parameters, fiber content and moisture percentage, elemental composition, and the carbon, hydrogen, and nitrogen, using analysis with an automatic sample. Carbohydrate, protein, lipid, and concentrations obtained through chemical analysis techniques. To facilitate the saccharification process and improve the fermentation efficiency, different enzymes were used. Liquefaction enzyme hydrolysis starts into the strain at high temperatures. Saccharification enzyme it breaks down the X-rays into glucose, which just ferment, and the viscosity reduction enzyme. This enzyme reduces the viscosity of the sweet potato mass, improving the efficiency of fermentation and processing.
This slide details the composition of the culture medium used in the preparing sample for fermentation. This medium is key for the growth of microorganisms and the efficient production of ethanol. The medium contains the following essential components for fermentation: glucose 100 g r per L, main source of carbon and energy. Yeast extract 8.5 gr per L provides essential nutrients and growth factor. Magnesium sulfate NGH of 4 to 7 H2O.1 gr per L. Key enzymatic cofactor in cellular metabolism. Calcium chloride KH L2.6 gr per L. Important for the stability of the cell wall. Ammonium sulfate NH42 2SO4 1.3 gr per L. Nitrogen sulfur might be hard growth. PA5 is maintained and acidic by loop. Zinc is optimal for enzymatic activity and efficient fermentation of microorganisms. Temperature of 30 degrees Celsius is ideal for this group and conversion of sugars into ethanol. Agitation guarantees a hot, genius use distribution of nutrients and of oxygen optimize fermentation. This culture mine has been designed to promote fermentation and maximize ethanol production from biomass. This slide illustrates the fermentation process of three different scale laboratory, pilot plant, and industry scale. Laboratory scale month 1. In the laboratory, the fermentation takes place in place of a small bacteria store. Here, the optimal conditions are studied through a spin height, temperature, and concentration of substrate. Small scale tests are carried out to understand the behavior of the microorganism before scaling the process. Key point: loss of flash and small reactor, visit temperature, and pH is controlled. Microbial performance analysis. Pilot plant is Mach 2. In this step, larger bioreactor with automatic control ID the viability of the process is tested before scaling into an industry level. This one has feeding pump to view the control medium is introduced. Agitation and erection system keys the measure homogeneity use and a CJT. Sensor that measure variable choose has pH, temperature and is J-chunk concentration thermal JK regulates the temperature of the system. Industry skill in my trade. In the last eight, fermentation is carried out in large capacity reactor. The process is optimal to minimize production and reduce cost. The key aspects are large reactor, large scale production for marketing, use of advanced control and monitoring technology. In us, the still is fundamental in the development of biotechnological products from laboratory research to large scale production is need to be optimal to share the efficiency and sustainability of the process. This slide presents the equation used to calculate the efficiency and speed of ethanol production in the fermentation process. It is based on the chemical reaction that describes the conversion of glucose in ethanol and carbon dioxide. This equation, alcoholic fermentation, where one molecule of glucose is converted into two molecules of ethanol and two of carbon dioxide, tend to the act of G. G1 measures the efficiency of fermentation compared the amount of ethanol obtained experimentally with the escape theoretic amount. G2 indicates how quickly ethanol is produced. It is calculated by dividing the final concentration obtained by the total fermentation time. Calculate this parameter is essential to optimize ethanol production, ensuring that the process is efficient and economic viable. In this three we seem to maximize E1 and I2 improve profitability.
Result in discussion characterization of the petrol after 100 grade centigrade for 2 hours is evaluation characterization carbohydrates, esters, glucose, sucrose, fructose, pH, average humidity, protein concentration, ash, fibers, lips, dry matter of the matter is component carbon, nitrogen, hydrogen, in others. The main conclusion from the experiments with the batch process is that higher ethanol yield can be obtained during the conversion of SSF from raw squid potato mash, which was is agreement with other past. The use of SSF could potential reduce the capital investment of a bioethanol production facility, since this process mode can be performed in one reactor instead of two reactors in the case of SHF and PSSF mode. The maximum ethanol concentration, supersaturation, and ethanol yield were obtained with an initial inoculum of 7%, which is economical and environmentally friendly. It was reported that increasing the just inoculum volume from 3% to 6% showed positive effects on the fermentation of 25% sucrose and reduced the fermentation time from 72 hours to 48 hours. However, excessive inoculum volume greatly influences the fermentation efficiency. Also added an amount of ammonium sulfate and silence to increase the ethanol yield and reduce the viscosity of sweet potato mash. The viscosity of potato mash decreased from about 10,000 to 500 centipoise in the first 90 minutes during SSF. On the other hand, the higher the pressure, the more dioxide carbon is dissolved in the fermenter, which could inhibit the fermentation of yeast. Cerevisiae, it makes sense to investigation the possibility of running a fermentation reactor under high pressure of different gases. As shown in table 2, no matter what gas we injected into the fermentation, dioxide of carbon, nitroxide, or air, if the pressure was below 0.3 megapascal, the theoretical ethanol yield was over 80% from 180 grams in little. Initial glucose concentration. uh, However, the fermentation time continues along with the pressures growing from 0.1 to 0.3 megapascal. When the pressure was 0.4 megapascal, the fermentation of yeast services absolutely stagnated after 34 hours. We call concluded that with the increasing pressure, the fermentation rate decreased. It was also established that at high concentration, dioxide of carbon can negatively affect microbial metabolism. The change of total reducing sugar in the final state of fermentation deeply influences the fermentation time, as everyone knows, along with amyl glucoside for saccharification starts become smaller and fermentable that carbohydrates such as glucose, fructose, and sugar evaporate. At the same time, is cerveza consumed the carbohydrates for bioethanol production. According to our HPLC, analysis. It is now that when glucose was used and fructose become the main fermentable sugar, we could mistake that the bioethanol production for raw sweet potato by ECF was terminal. From the result, we can see that the ethanol productivity yield with raw sweet potato puree was comparable with cassava starch. The preferred situation in an industrial setting is to have a single microorganism capable of consuming all sugar simulation and the high rates in a medium which could be achieved in a shorter fermentation time, thus improving volumetric productivity. The advantage of using sweet potato as a feedstock for the bioethanol production, especially on an industrial scale, is that it can consider ethanol concentration, yield, fermentation time, and ethanol productivity rate. Currently, the vinasse produced at the Indo test plant is being concentration and fermentation to produce organic fertilizer, and the liquid fast could not be treated as a common water due to its high organic load. The use of the liquid phase as a feedstock for other fermentation process is being investigated.
Conclusion 1. Sweet potato is by a bulk-free stock for bioethanol production as it provides the right nutrient and hydrogen balance for fermentation. 2. The use of silanase significantly reduces the viscosity of raw sweet potato puree facility is processing and improving fermentation efficiency. 3. The concentration of ethanol obtained in the fermentation was comparable to that of other grain-based by of ethanol, demonstrating its economy and environment viability. 4. The SF process allows high ethanol yield to be obtained without the need for additional PA adjustment, simplified in large-scale production. 5. Scaling the laboratory process to an industry scale should positive result, maintaining efficiency in ethanol production. 6. Chemical, oxygen demand, and final viscosity were efficient, culture reducing huge treatment costs. 7. BSF process simplified fermentation combining saccharification and conversion of sugar to ethanol in single step reduced cost and time. 8. The result obtained support the viability of use roasted potatoes as resource for the production of bioethanol at an industry level, offering an efficient and sustainable